Hi, my name is Fernando Moya and this is Eric Altaman, and today we are going to present to you our submission to the ARDUOUS workshop. This is called Retrieval-based Annotation of Multi-Channel Time Series Data for Human Activity Recognition, and our submission to the ARDUOUS challenge. Human activity recognition classifies sequential data of humans performing a certain activity. This is a core. It's very important for different applications in medical, health, and industrial application for optimization. Independently on the method or independently on the application, one always is bound to have annotated data or to have annotated data for certain training of a classifier. For annotation of a data, usually a human will be presented to let's say a window of measurements of a human performing an activity. In this case, it will be or a video or a, let's say, skeleton or a certain model of the human doing or performing some activity, and the annotator has to give or provide information about the activity or other information what is happening in the performing of the activity. Other methods rely on a semi-automatic annotation or automatic annotation where a model classifies directly the entire sequence, and a human, in this case the annotator, will be having the task of the revision, let's say cleaning up the noisy annotations of the model. However, this process is very demanding, it's very time consuming and very exhausting. And they have been worked on, let's say, on annotating 1 minute of data, taking around 45-50 minutes of annotation time. For example, in the case of annotation for activity recognition in warehousing, manual annotation and automatic annotation have already been investigated. Manual annotation and semi-automatic annotation have been already investigated for let's say creating activities creating annotation for activity recognition. For example, here previous work of us, an annotator was visualizing the skeleton of a person performing certain activities in a warehouse, and the annotator has to kind of like select the ending of the frame or how long this, let's say, activity is happening, and select the class information and some semantic additional information that the subject does, if it's using the right or the left hand or the both hands or a certain object. This has to kind of like go in an order fashion, so looking at the entire recording and start stopping the recording and observing what's happening. So the annotator has to constantly paying attention of what is happening in the entire recording. This usually takes a lot of time for this, let's say, for this data set. An annotator took around 40-50 minutes per minute of recorded material. And yeah, kind of like reported exhausting, let's say, as this is an exhausting task. And also they reported eventually the annotators having a lot of breaks in between, need to have a lot of, let's say, concentration for fulfilling this task. In the case of semi-automatic annotation, at least for this example, a neural network will be classifying the entire sequence at first. And eventually then the annotator selects what kind of the annotation wanna keep. And going time-wise, like through the entire recording, and let's say correcting what the network did. In this case, correcting the activity or correcting the semantic information that the network was able to provide. This is, let's say, half or show it to half the annotation time, and the person was kind of like less exhausted after the annotation of the entire recording, and only has to kind of like go and focus on the network was extremely wrong based on the semantic information or based on some kind of like context. What happens that if you know that already a class was happening with, let's say, walking, eventually that person will keep walking, or if it's getting an object, will be, let's say, moving with certain hand and so on. So that the annotator had a little bit easier to do the process. However, the annotators still need to go through the entire recording to improve or to correct these noisy labels, and it still is time demanding.
So right now I will explain a bit about human activity retrieval. Imagine we want to look for segments that contain an activity where the person is doing something above their head with their arms. In that case, the first two clips that you see would be more similar to each other, and the query that we want. Then the third picture, where the subject is handling centered, even though the second and third might have in common that both are done by subject B. The basic pipeline for human activity retrieval will be that you take human pose, motion capture data or IMU data, you put it through a model, in our case a neural network, and you get a kind of representation out of it. And then you compute that representation to a representation of the thing that you want using a similarity metric, and then you order all these segments according to that similarity. You can sort it by different means, depending on what you want at the moment. Either you sort them by activity classes, or semantic information, or combinations of semantic information in the center. And you compare the similarities using different similarity metrics. For example, with the quotient similarity, you mentioned that these semantic information is a vector in vector space, and you can compute the angle between them. Or you imagine that the semantic information is a random variable, or many of them, and you compute the probabilities that they are similar to each other. What we did first with human activity retrieval is we've evaluated it globally on a dataset, and then we performed an annotation task using the retrieval on a subset of the data task. The data set in question is the LARA Dataset. It contains activities, or as we call them, classes, which are among others standing, walking, moving a cart around, and 3 different types of handling depending on your body and arm position, whether it's above your head, in front of your body, or whether you have, or whether it's at your feet. Then there is a subcategorization, what I've called earlier semantic information, we call attributes, and it is what the activities can be separated into. For example, in the first group, in the top left corner, is it is separated into gait cycle, or I guess walking, into taking a step or standing. Same way in the third group below that, you can have either an action performed with your left hand, or with your right hand, or with both hands at the same time, or without any hands. For example, if you just walk around carrying nothing, you would choose no hands because you aren't using them with an intention to do something. To evaluate the retrieval globally, we use what's called average precision. Of any given list of segments, it evaluates how well it is sorted, how many of the relevant segments that we want to see are at the front of the list. The closer it is to being well sorted, the higher the value. Then we take the mean of the average precision per recording, where we go through each query and divide by the sum up the average precisions and divide by the number of queries. And then we take these mean average precision values for single recordings, sum them up again, and divide them by the number of recordings. The first thing we did was to compare different segmentation sizes with the two similarity metrics that we have, and compare query by attribute representations, which are combinations of attributes, against query by classes. And we can see here that the values for query by class are pretty good, with values of above 0.6. In contrast, query by attribute representations are not as good. But if we compare the attribute representations with single attributes, we can see here that the mean average precision values are very good. And this shows us that it is feasible to use retrieval in a productive manner. Next, we wanted to try annotating using retrieval. To do that, we take the expansion to LARA, which includes subjects 15 and 16, and we follow the annotation procedure of the previous paper, which we presented last year. And to do the annotation, we have 4 annotators, 2 of which are experts and 2 of which are beginners. And in total, we annotate 8 recordings. To make the retrieval annotation possible, we have taken our tool and we have made an update for it to include a retrieval mode. To use it, the annotator has first to do the automatic annotation, where they choose a network and forward the recording through it. And after the network has segmented and annotated it, the human annotator can switch to the retrieval mode, choose a distance, choose a class of which to start with, and then they can start annotating by either clicking the accept button or the reject button based on that small video segment that they can see. Here we can see the results of the annotation task, mainly the time it took. We compare the probabilistic retrieval mode against the cosine similarity and against the pure manual annotation time. And as you can see, the time it took to annotate was cut approximately in half, while at the same time the consistency measured in Cohen's kappa has remained high, which means that the annotation effort went down while the quality of the annotation stayed the same, and that is a very good sign. We have also had reports by our annotators that they experienced less mental strain during the annotations, and they didn't take any breaks within a recording. And for individual attributes, the consistency also stayed up. except for maybe the step attribute, where some annotators might have put down gate cycle and others might have put standing still instead. So to summarize, I've presented human activity retrieval to you. It sorts a list of segments based on a selected activity query. The annotation effort is reduced without compromising consistency, and the annotators felt less mental strain because they only had to click 2 buttons. That was my part about human activity retrieval, and now Fernando is again going to present to you about the ARDUOUS challenge.
Thank you so much, Eric. So, regarding the ARDUOUS challenge, the idea of the challenge is to demonstrate solution for annotating the CMU kitchen database. In this case, there are two, let's say, modes of the annotation: the manual annotation or a semi-supervised or automatic annotation. The kitchen dataset is a subset of the CMU multimodal activity database, and it consists of recordings of humans preparing some recipes, in this case brownie, sandwich, or eggs. And we have recordings from, or material like data, recordings of video, on-body devices, motion capturing system, and let's say additional cues of material. For the challenge, we were only allowed to use the video to sets of on-body devices and RFI data. And for the manual annotation, for both annotation, the idea is to annotate the 4 runs per recipe. And for the semi-automatic annotation, they also provide the runs for the training set and for the testing set. Before, as submission, let's say we are commanded to submit the recordings in a certain format, which is a TXT file which have the annotator, the data time, the annotation, the class, the file, and starting, ending, and of the window, let's say the specific segment of the recording. And there will be a measurement of the precision, recall, accuracy, and F1 according to the, let's say, the annotation provided by us. Before adapting or providing a solution for the manual or the semi-automatic annotation, we first analyze what it was provided by the CMU kitchen database or the dataset and their annotation. And the challenge provided, let's say, a list of the different activities and all the articles and places that the person visited or showed while doing the 3 recipes. And in this case, we try to feed this, let's say, annotation or this representation or this information into our semantics that we have already used or explained it before. In this case, it's an attribute representation. And for that, we also follow a sort of sentence structure where the person will be doing, let's say, a verb will be an action, will be using an article, that will be the first object, probably using a second article according to the activity, so will be a secondary object, and will be also denoted by later a place, either way where the article is taken from or put into or on, and eventually a temporal information, which is like partially or fulfill activity. Following this, we decided to have these 4 categories for our attribute representation, or in this case category, we call it groups. This is an example of the groups that we have, and then say in the left side we have all the lists of the activities that are provided in the CMU kitchen database, and all the 4 groups that we have: the first object, the second object, let's say the place or third object, and eventually the temporal information. And according to how more or less like the occurrence of the objects per class, we decided a sort of rules for the attribute representation of these kind of groups. So when a person or the annotator will select a certain activity or a verb, only the list of the attributes that are appearing or are common for that action will be listed for the annotator. In this case, the annotator doesn't have to go and look for a huge amount of articles or places in order to select, but rather more for the articles that are or are expecting to be in the annotation. This is based, of course, on the rules of the challenge. We adapted our annotation tool, the one that was previously presented with the retrieval, in order to show or to, in order to load, let's say, a video from the kitchen database. We selected one of the views in which the subject sees, like the ego view of the subject. And the idea will be that the user will be loading the video and start, let's say, setting the ending of each frame and selecting the classes and eventually all of the attributes that are happening in the sequence or in the activity while performing a recipe. Yeah, so the idea is like we adapted our annotation tool in order to load the kitchen database. And for that, the user will be selecting one of the videos for the runs of that are requested for the challenge, and the annotation tool will adapt in order to load that video. In this case, the annotator will not be looking at the skeleton from the motion capturing system, but rather the egocentric view of the subject. And pretty much the annotator has to go and select the ending of the window, of the ending of the certain small activity, and go and select the labels. And the labels will be following, as I say, this sentence structure that we propose, based on the attribute representation also that we are proposing. And in that case, the sentence will follow an activity, which will be the verb, and the different objects, the object number 1, the object number 2, object eventually number 3, and this temporal information that is added in one of the annotations. This case is quite simplistic for the annotator to follow the labels, as it follows a very quite logic from a grammatical sentence. The person will be opening the fridge, and from the fridge will extract certain object and put it somewhere else. Or the person will go from place A to place B. Or the person will take the X, that will be object 1, and put them into the pen, that will be the object number 2. And it says partially. In some point, the person is steering, so it will be steer. We'll be using some steer object and then start mixing. And eventually, partially means that it probably not fulfilled the task. And this is kind of like the order that we presented to the annotator. And pretty much that's it. Next step, what we continue was to annotate all of these for runs per recipe, and trying to measure how much time the person or the annotator spent fulfilling the entire annotation. Interestingly, as I say, according to the labels and according to the activity and according also to the recipe, the object, the list of objects, the list of the attributes changes. So it's not like all the objects, not all the attributes will be listed for the annotator to select. It will be only the attributes that are related to the class. So it's quite simplistic when you say, hey, let's say, cutting something, eventually will be happening in an object that is the knife. Or if I take something, will be either way the bread, or the spoon, or the X. Or if I walk, then will not be any article. It will be probably a place. Then it will go for A to B. And this is quite simplistic to follow. We experienced different difficulties when adapting our annotation tool to the kitchen dataset. One of them was the synchronization between the different view perspectives. So there were different views, let's say, for the provided by the challenge, but we adapted only the egocentric one. And it will be better if we can have synchronized version for all of the videos in which every time the person wanted to, let's say, stop or annotate a specific segment, that the annotator can select different perspectives that are of course synchronized and see what is happening in that video. Because some article, some object could be occluded based on the camera position, the camera perspective, or just by the movement or by the subject when it's performing the activity. When it's opening a door or opening a drawer, we don't see what is behind or what is in the hands. So this was a little bit difficult to achieve. And also similarly with the on-body devices. The on-body devices were not necessarily synchronized with the videos and with the annotation. So when performing semi-automatic annotation, when we wanted to train a model for the semi-automatic annotation using retrieval with the on-body devices, we were not able to achieve it as the video and the on-body devices were not synchronized. We were able to fulfill manual annotation using our annotation tool. In this case, the annotator was annotating the 4 runs per recipe and recording the annotation time, the starting, the stopping, and the break of the process, and also some revision, as the annotation tool offers the option to do a revision of the entire sequence. We noticed that the annotator experienced some learning while doing the annotation per run. So every time the runs, there was a new run, the annotator took lesser time in fulfilling the task. And we also see that the brownie took way much time than the annotating the sandwich of the X recipes. So the brownies took 1 hour, around 1 hour for annotating each run, and the sandwich 20-30 minutes. But in general, it was possible to do the annotation of the kitchen dataset with our annotation tool using the logic, the sentence that we proposed for the activities and the objects, for all of the object 1, 2, and 3, and the temporal part. And the annotator was able to do the annotation without much, let's say, effort, as it was kind of like following a logic of our annotation tool for the LARA dataset. As explained before, we had some difficulties on working for the semi-automatic annotation using on-body devices, because the on-body devices were not synchronized, also not synchronized with the annotation. So the training material, at least for the on-body devices, were not successfully useful for us. So we trained a neural network based on different segmentation sizes. We also used transfer learning. We adapted a network based on LARA, based on other data set, and we were not able to achieve that the network trained. There is not even achieving a certain average performance, not even random. And, this kind of like give us a sort of feeling that something is happening more with respect to the data, with if our synchronization for all of the sensors, for all of the windows that we have, are well done. So this is one of the difficulties that we have seen when trying to provide a solution with the semi-automatic annotation. However, having in the future sort of segmentation and sort of synchronization for all of the on-body devices, and a model that is trained based on the training material, we could adapt also our annotation tool using the retrieval mode for annotating the kitchen dataset, and of course providing probably a sort of boosting on the annotation time. We also expect, or also in the future, to do or train a model based on the video. So let's say a video-based neural network that will be used as classifier in order to compute this embedding for the distance in the between a query and the specific windows, if we want to use this for the retrieval mode. But this is more or less future work for the challenge. In general, in conclusion, we submit some solution for the ARDUOUS challenge, or the manual. We submit the manual annotation for the ARDUOUS challenge, in which we adapted our annotation tool, also based on sort of attribute representation and sort of based on a sentence logic for annotating the kitchen. And an annotator was able to annotate all of the 4 runs per recipe for the 3 recipes that we provided, with average time for the brownies for 1 hour, 30 minutes and 20 minutes for the sandwiches and the eggs recipe, and the attribute representation based on the data dictionary that was provided by the challenge was successful, was kind of easy to understand by the annotator. We also provided, or we tried to provide a solution for the semi-automatic annotation of the challenge using a neural network on the on-body devices. However, we were not able to succeed. We guess, or we think, that this is mainly because of the synchronization of the on-body devices and the videos and the annotation for the training and the testing set. This is it. Thank you very much for the opportunity of having us in the ARDUOUS workshop. Thank you also for my group, for Eric, to Nila, to Eugen, and Professor Fink for all the collaboration for the submission for the work for the ARDUOUS workshop and for the ARDUOUS challenge.